More than 90% of the world's supply of this metal comes from a handful of mines, and every single touchscreen ever made depends on that fragile trickle. You tap it, swipe it, and scroll it thousands of times a day without ever wondering what actually lets your finger command the glass. The answer is a soft, silvery element most people have never once said out loud. Its name is indium. Indium sits quietly on the periodic table, sandwiched between the metals nobody talks about. It is softer than lead and rare enough that all the indium ever refined would barely fill a few swimming pools. Yet without it, the flat glowing screens that define modern life would simply not work. Here is the trick that made indium irreplaceable. Compound it with oxygen and tin, and you get indium tin oxide, a strange substance that is both transparent like glass and conductive like metal. Almost nothing else in nature does both at once. That contradiction is the whole reason touchscreens exist. A capacitive screen works by sensing the tiny electrical disturbance your finger makes when it nears the surface. To do that, the glass needs an invisible grid of conductors laid across every part of it. Indium tin oxide is that grid, coated in a layer so thin it is measured in atoms. The coating is applied through a process called sputtering, where a solid target of indium tin oxide is bombarded in a vacuum until atoms fly off and settle onto the glass like an invisible mist. Every phone screen, every laptop, every television and car dashboard passes through a machine that does exactly this. So where does all this indium come from? Almost nobody mines it directly. There is no great indium mine anywhere on Earth. Instead, indium is a ghost that rides along inside another metal. It hides in the ore of zinc, present in quantities so small that a ton of zinc ore might yield just a few grams of it. The only way to get indium is to already be smelting zinc at enormous scale and to bother capturing the trace that would otherwise be thrown away. This is why the map of indium is so lopsided. The metal follows zinc production, and zinc refining is dominated by a small number of countries. China alone accounts for the majority of the world's refined indium, with South Korea, Japan, and Canada making up much of the rest. That concentration is the fragile trickle from the opening. When a handful of smelters in one part of the world control the flow of a metal that every screen depends on, the whole global supply hangs on decisions made very far from the factories that assemble your phone. The vulnerability is not just theoretical. In 2005, when China first began tightening exports of certain strategic metals, indium prices lurched upward almost overnight. Manufacturers watched a component they had always taken for granted suddenly become a bargaining chip in a much larger game. Governments took notice. Indium now appears on the critical minerals lists of the United States, the European Union, and Japan, alongside the rare earths that make headlines. But unlike those, indium has almost no domestic source in most of the countries that depend on it most. There's a second, quieter problem. The world burns through indium far faster than it recovers any of it. Most of the coating sputtered onto glass never even reaches the screen. It lands on the walls of the machine and is scraped away as waste. Recycling rates for indium in finished electronics remain stubbornly low because separating a few atoms of metal from a shattered phone is brutally difficult. All of this raises an obvious question. If indium is scarce, geographically concentrated and hard to recycle, why not simply replace it? Engineers have been trying for years. The candidates read like a wish list. Silver nanowires so thin they let light pass between them. Sheets of carbon just one atom thick, called graphene. Networks of tiny carbon tubes and printed metal meshes. Each one promises to do the job of indium tin oxide without the indium. But indium tin oxide has been refined for decades, and it is remarkably good at its job. The alternatives tend to be more expensive, harder to manufacture at scale, or slightly worse in one property that matters, like clarity or durability. Replacing a mature material embedded in trillions of dollars of production lines is far harder than inventing a better one in a lab. There has been progress. Flexible and foldable screens, where brittle indium tin oxide tends to crack, have pushed some makers towards silver nanowires and other bendable conductors. In those niches, the reign of indium is genuinely slipping. Yet for the flat, rigid screens that still make up the overwhelming majority of devices sold, indium tin oxide remains the default. Decades after engineers began looking for the exit, the industry is still overwhelmingly locked in. So the strange arithmetic holds. A metal almost nobody has heard of, produced as an afterthought of zinc refining, controlled by a small cluster of smelters, coats the surface of nearly every screen humanity looks at each day. The device in your hand is, in a very real sense, downstream of a zinc mine you will never see. The next time your finger glides across glass and the screen answers instantly, remember what makes that possible. Not just the software, not just the chip, but an invisible film of a rare, borrowed metal, riding a supply chain so thin and so concentrated that a single decision in a distant refinery could ripple all the way to the phone in your pocket.
If you found this deep dive valuable, hit the like button, drop a comment below on what tech mystery we should decode next, and subscribe to never miss an episode.